this.
Hello, is it working? Hello, is it working? Can you hear that? Hello, that's better. Good morning. Did you see the cricket yesterday?
Yes, sir.
Not a T20, it's a E8. India, it's not supposed to rain in India, only in England. Yeah, that's it. So, this morning we're going to, I'm going to try and get you to do the first design, or think about the most difficult part. We're going to do 2 designs before the tea break, hopefully. The first one, fairly straightforward, but the first part, quite difficult. And then the second one, more complex design. Then we'll have the tea break. And after the tea break, we'll look at the hazards and the races, which is very important for all design. So I'm going to draw waveforms up. There's 1 input, 1 output. And if you're using fundamental mode asynchronous design, I want you to try and assign the states. Okay? States to this set of waveforms. I'm going to give you a few minutes to do that. And I'll guarantee that most of you will make 1 mistake. Hopefully, you never know, you might be geniuses. But this is why we come to learn. Because this example is deliberately set. So remember, each state has to be unique, but we want to assign the minimum number of states to the waveform. If you're a novice, you could go through this and say every change in input, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, you could put 11 states in there. Then you're going to make your job a lot harder. I can tell you it's less than 11. That's my clue. In fact, it's less than half. The second clue. So there's the input. So 1 input. It's a sort of clock-type waveform, but in asynchronous, the clock doesn't have to be a clock. As long as it's 0, 1, 0, 1, 0, 1, the spacing could be different. So the output here, so it starts low. We've decided that. Then it's going to stay high for 3 half pulses. Then it's going to go low for 1 half pulse, and stay high for 3 half pulses, low for 1 half pulse, and so on. So it's a repetitive output. Okay, so I want you to try and specify the states. So I've put up the circuit design procedures on the slide there for this type of circuit. So number 1 we've defined the inputs and outputs. As engineers, you might have to do that for yourself. Or in this case, I've given you the design spec there. Okay? So the hardest part of this is the next part, which is number 2 on the list. Assign unique states to the set of waveforms. Then the rest of it is a bit more mechanical, because we've got to draw the state tables from these states, look at the combinations, reduce the tables down. As you saw yesterday, we signed the secondary states, produce Carnot maps for the final gate design. And at that point, you could build the circuit in hardware, you could put it on a simulator, apply these waveforms, make sure it works. Okay, so I'll just draw a number of states. So remember, we draw the state in the middle because it's a level change, not on the edge. So I'll just put down a number of states. And I want you to assign the numbers. Okay, so So just put the first few down there. So just take a couple of minutes yourselves and try and assign numbers to these states. Okay, so we start with 1 and so on. So we're going to go 1, 2, and 3, and whatever else. So you can see it's repetitive, so that's telling you when you get somewhere down here, you're probably going back into some of the similar states, because we repeat. So, a clue there. So when you've finished, you can tell me how many states you've got. 3. Anyone got more than 3? Anyone got less than 3? Anyone not got any? Do you know what I'm asking you to do? Because this is a crucial point. You okay? So we're going sequential order. State 1, state 2, but every state has to be unique. 3, unfortunately, is the wrong answer. 2. That's impossible. 4. Who said 4? Why? Yes. Four, yeah. And then what's this state then? Top of the class, well done. He's got the right answer. It's a deliberate example to make you think. And you can think about it a number of ways. So let me just put it on the board, then we can discuss if you don't follow. So it's simplified in terms of input. The first input, we're going from 0 to 1 and the output changes, so that's got to be a new state, okay? And I designed it deliberately to try and, it's not wrong that you got 3, don't worry, 100% in UK will get 3. So then you got 3, because we've got the input's low, but the output's high again. Now when I'm trying to think about these types of circuits, they've got memory. So what we're trying to do really is what my friend said there, we're counting 1, 2, 3, 4 half pulses before it changes. This state here, inputs 1, outputs 1, looked exactly the same as state 2. Okay, but what happens if we're in state 2 and the output goes low again? No change in output. So the circuit's counted effectively. So when we got this one, the fourth one, effectively circuit feedback has said next time we have a pulse going low, we're going back to state 1. And then the sequence will repeat. So we can stop there because we know it's just got 4 states. Do you all see that? Because it is tricky. You all okay? So that's the hard part of this morning on this first question. Now we have to train ourselves, it's a bit more like textbook engineering up to a point, how to produce the circuit from here. So from there we have to draw the state tables. I'll try and do it on the side because the state tables are longer and thin this time because we've only got 1 input, so we can only have a 0 or a 1 on the input, but we've got 4 rows. So I'll try and squeeze it in on the end over here. So we have an input state table and an output state table. So remember, we list the inputs down the columns. We've only got one input, x, so we only have two columns this time. Yesterday's example, we had two inputs, so we had four columns. We've got one output, z, which is going in this table. All the inputs are going in here. So we start in initial conditions. X is 0 and the output is 0. So we call this state 1 and the output is 0. Okay, remember one stable state per line. So on the second row, we got state 2. How do we go to state 2? Well, x goes from 0 to 1. So that's the transition state 2, which tells us where we're going to. And we arrive in the stable state 2. The output is 0 in stable state 2. Sorry, the output is 1 in stable state 2. So that transition state is effectively the edge, the changeover region on the output. So we put a dash in. Okay, so that's the first transition. Then the input goes from 1 back to 0. We're going into stable state 3, so we put a transition state 3 in there to point us where to go. This time both the stable states have a 1 on the output, so we make the transition state 1 to maintain the output. We don't want this output going anywhere when we change the level. And the next one, 3 to 4, we're now going on the input, 0 to 1. So 0 back to 1, 3 to 4. So there's the transition state 4 to tell us where we're going. 3 to 4, both stable states are 1, so we'll make the transition state 1 to keep the output high. Then the final one, the input goes from 1 to 0. The output's going from 1 to 0. We're going from state 4 to 1. So we're going from 1 to 0 on the output, so we make that state unspecified, which will become a don't care eventually. So, new thing today, implication table. Okay? Yes, yeah. With X? No, output state table, it's output Z, but X is the input. Yeah. So these are input states, these are the states, and the output Z state table, these are the outputs here in the table. These are the inputs down the column. Yeah, but good question, because it's complicated. So the next thing is the most complicated thing, the implication table. Okay, so there's a set of rules for the implication table, which I didn't want to write on the board. So I typed it in my office at home. So before we do the implication table, this is how we look at this input state table with the output state table, say, can we combine any states like we did yesterday? Remember yesterday we combined 1 and 2 into state 1, 3 and 4 into state 3. Well, what's the rules? Well, there's a yes, a no, and there's these implied combinations, or implied combinations. All the combinations down the columns. It's not too bad in this case, we've only got 2 columns, we've got 4 columns. In the next example, it's slightly more difficult. So, yes, we can do a combination if you've got 2 rows can be combined under the following 2 stable states with the same output in the same column. Same column means the same inputs. So, for example, state 1 and state 3 are in the same column, but we've got different outputs. So that can't be a yes. If they both had an output of 1, we could, in that column, they could be combined, but it has to be for all the columns. If you've got 2 columns or 4 columns, and we agree on, or disagree on one of the columns, you can't combine. So it's quite complicated, quite complicated to get your head around. So any combination with an empty state. Well, in this example, we haven't got any empty states, but we did yesterday. You can combine, in this design, anything with nothing. Then the stable state with transition state are the same number. Well, this is what we did yesterday. Someone asked the question, if we were going to combine these 2 rows, for example, transition state 2 and stable state 2 are nearly the same anyway. It's moving towards that state. And even if the output changes, we can combine it, and the stable state output will override the don't care. So if you were to combine these two rows, 2 and transition state 2, the output will become a 1. But the bad news is, on this circuit, it's because for the way it's sequenced, we can't combine any state. Because as we found out, we're counting 4 states, and we go to 1. So I know before we start we can't, but we're doing the exercise. So in the next example, we can do it. So that's for yes. So any of those means you can combine states. No, 2 rows can be combined due to conflict. So 2 stable states with different outputs in the same column. So this is what I'll say. Well, let's look, 1 and 3 again. 1 and 3. 2 stable states, same column means same inputs, different outputs, you can't do it. If you look at the other 2 stable states, 2 and 4, in the input x equals 1 column, both their outputs are the same. So on that column, you could combine them. But when we look at 2 and 4, you have to look at 1 and 3 as well. And 1 and 3 we'll find out can't be combined. So nothing can be combined, but you don't know that yet. So this is impossible because you physically can't realize that as your circuit. So that's for no. And these are the implied ones, which is why we draw this implication table. And maybe you can't make a decision on it. So a stable and transition state of a different number. So, for example, if you wanted to combine the top row and the bottom row, in this column you've got a stable state 4 and a transition state 2. That's a number. You have to, in our implication table, we can't make a decision on that until we look at if stable state 2 and 4 can be designed in a different box. 2 transition states of different numbers. So again, we could look in this column, we combine in this column with this, we've got state 1 and state 3, transition states. That's only implied. You only make the decision on the stable states. And the last one, this is very important. 2 stable states with different outputs can be combined if they exist in different columns. So that means we've got different inputs. So that's different from being in the same column. Anyway, this will take a stand straight away. So I'll draw up the table. I'll take out. So when we draw this implication table, it's important you know how to number it. Because it's like a road atlas. You don't want to find how far it is from Allahabad to Allahabad. You might want to find out how far it is from Allahabad to Delhi or Allahabad to Jaipur. So you have to number this in reverse order that way and in forward order that way. So we have all the possible combinations here. So for example, in this first one, we're going to look at state 1 with 2, 3 and 4 in different squares. And the next one, we'll look at combination of state 2 with states 2 and 3, and then the final one, state 3 and state 4. So all the combinations should be covered in that table. We call this implication table. Okay, you ready to go? Yeah, so first one, start at the top, state 1 and state 2. Can we combine them? So we're looking at the top 2 rows. So we mask out the others, we're not interested in the other rows. We're just looking at state 1 row, which is stable state 1, and state 2 row. So we have to look at it column by column.